Hello, friends. Today, I would like to discuss about the liquefaction phenomenon. As you have seen recently in Myanmar and in Bangkok, that many buildings, many tall structures in Myanmar, in Thailand, they collapsed just like a pack of cards. And the reason was given that it was due to liquefaction. So, what is this liquefaction phenomena? How you can find out the liquefaction potential of a site by performing simple field test, and how to prevent this kind of catastrophic failure. So, today our topic is related to the liquefaction phenomena. As the name suggests, that liquefaction is related with the ground becoming liquid. Just it loses all its strength. How it becomes? If at a site, let's say this is the ground surface, and you want to find out the liquefaction potential of this site, you can do it very easily by performing certain field test. But first, what is liquefaction phenomena? When there is going to be earthquake, what is going to happen that when there is going to be earthquake, the ground, if it is fully saturated and it is a cohesionless ground, the soil is cohesionless, then you will find that due to earthquake, the pore water pressure is going to shoot up. It is going to increase. And because during earthquake, you will find that the shear stresses are going to be so fast with respect to the time that with each cycle of this earthquake force, your pore water pressure keeps on building. As a result, if you go below the ground surface at any point, let's say at any point here, if I consider this point P, the effective overburden pressure at P at any point below the ground level in a saturated soil mass, sigma naught prime will be equal to the total overburden pressure minus the pore water pressure. Now, what happens during earthquake because of the dynamic force, because of the shear stress induced in the soil mass, the excess pore water pressure keeps on building. So, U keeps on building, keeps on increasing with each cycle, and it's not able to dissipate. Because it is not able to dissipate, the excess pore water pressure U will keep on increasing. But the total overburden pressure sigma naught doesn't change, because this is going to be equal to the saturated unit weight multiplied by depth Z. So if the unit weight of this ground is gamma sat, this is the total overburden pressure. Therefore, the effective overburden pressure is going to be, now here gamma sat is constant, there is no change, and at a particular depth Z is also constant. So this sigma naught doesn't change at a particular point, minus the pore water pressure is increasing. And when this pore water pressure becomes equal to the total overburden pressure, the effective overburden pressure becomes 0. And the moment the effective overburden pressure becomes 0, the supporting capability of the ground becomes 0. The bearing capacity becomes 0. And therefore, any structure that you have built up over the ground, it has no supporting capability. And therefore, in Myanmar, recently, due to liquefaction, the whole structure have collapsed. That you have witnessed on 28th of March when there was earthquake. The liquefaction phenomena have created havocs not only in Myanmar but also in Bangkok, in Thailand. So you see that the effective overburden pressure, when it becomes 0, the supporting capability of the ground becomes 0, and the soil liquefies. Therefore, the soil liquefies. And this phenomenon is called liquefaction. So liquefaction is very dangerous when there is any dynamic force, maybe due to pile driving or due to earthquake or due to any reason. If the loading is going to be dynamic in nature, it can create havoc for your structure that you have built it. So what happens during the earthquake? That let's understand it. Let's say I consider this ground surface, and At a particular depth, let's consider a soil element here. Say at depth Z, the soil element. This soil element is subjected to, let's say this is fully saturated and unit weight is known to you. So you can find out this soil element will be subjected to the total overburden pressure. And the horizontal pressure is going to be equal to, at rest condition, it will be K naught, the coefficient of earth pressure at rest, multiplied by K naught. So this is the horizontal pressure, confining pressure. The ground is level. This is the force. Now, in level ground, this is the position at rest condition. Now, if the earthquake is going to strike, due to earthquake, what is going to happen? This soil element now is subjected to the overburden, the confining pressure, and due to this earthquake, what is going to happen is you are going to have a shear force that will come into picture. So here there is going to be, with this cycle, the shear stress due to earthquake with respect to time. So now here there is going to be shear stress. This shear stress that is going to develop will try to induce a clockwise moment, which will be resisted by anti-clockwise moment. So here you can see that this element will get distorted. The shape of the element, this element, because of the shear, will be like this. This is now subjected to, due to earthquake, not only the overburden pressure, but it is also subjected to the shearing stress. Isn't it? It gets distorted. So, if you, this is the peak ground acceleration. If you find out the tau average, the average shear stress, then this tau average divided by, if it is effective overburden pressure, if it is effective, then tau average divided by this effective overburden pressure is called the cyclic stress ratio. Now, depending upon the resistance offered by the ground, what is the resistance offered by the ground? So, tau, that is the shearing resistance offered by the ground divided by the effective overburden pressure. We call it cyclic resistance ratio. We call it CRR, and this is called CSR, cyclic stress ratio. The cyclic stress ratio is due to the earthquake, and this cyclic resistance ratio is the resistance offered by the ground. And if cyclic resistance ratio is greater than the cyclic stress ratio CSR, then there will be no liquefaction. But if the cyclic stress ratio equals to or it is more than the cyclic resistance ratio, the ground is going to liquefy it. So this ground will liquefy the moment you find that CSR, if the cyclic stress ratio CSR, this one, is greater than or equal to CRR, the cyclic resistance ratio, then ground will liquefy. Liquefy. Now, normally the liquefaction phenomena is going to take place if it is going to be fine sand, saturated, fine sand, or silt, silty soil, where when there is going to be earthquake motions, the ground is going to have the loading in the form of shear stresses, then the excess pore water pressure that is going to build up in the saturated soil mass is not going to escape in fine sand or in silty soil, resulting into building of excess pore water pressure. And this excess pore water pressure, when it becomes equal to the total overburden pressure, then this leads to effective overburden pressure equal to 0. And the ground is going to liquefy. So your structure is bound to fail. And that is what happened in the recent earthquake in Myanmar and in Bangkok. Even during Bhuj earthquake in 2002, many grounds which were near the Sabarmati river, they also got liquefied. So your supporting capability becomes practically zero, nil, and the ground is going to liquefy. So this is all about the liquefaction phenomena. So you know that the type of soil is very important. Also, the soil is going to be in loose condition. So, when the relative density of the soil or of the ground is going to be less than 65%, it's not in dense condition. If it is not in dense condition, then liquefaction phenomena can take place. But in dense condition, it doesn't take place. So for liquefaction phenomena, relative density is important, soil type is important, groundwater table is also important, because the soil mass is fully saturated, then only the voids will be completely filled with water. And if the voids are completely filled with water, the excess pore water pressure is going to build up, resulting into liquefaction. So groundwater table is also very important. And also the earthquake characteristic. So what is the earthquake characteristics? This will also influence the liquefaction phenomena at a site. What is the duration of this earthquake? What is the frequency? What is the peak ground acceleration? These are very, very important. What is the magnitude of the earthquake? That's also important. So, these things are going to influence. So, when you are going for constructing any structure at a particular site, it is mandatory for the site engineer to get the soil tested, and you should try to determine the liquefaction potential. Whether the ground is susceptible to liquefaction, if it is susceptible to liquefaction, then you will have to take remedial measures. In my next video, how to find out whether a ground is liquefiable or not, what test we should do, and how to analyze it. Once you find that a particular site is going to liquefy if there is an earthquake of certain magnitude, and you know the maximum or peak ground acceleration, and you find that this ground is going to liquefy, then you can go for certain ground improvement techniques. You can make the ground non-liquefiable. A liquefiable ground can be made non-liquefiable before construction, so that even if the earthquake strikes, your ground doesn't liquefy and there is no catastrophic failure of your structure. Very, very important that you should analyze and find out the liquefaction potential, whether ground is susceptible to liquefaction or not. If it is not liquefiable, there is nothing to worry about. But if it is liquefiable, then you must take remedial measures. You should resort to ground improvement techniques and make the ground non-liquefiable. So, a brief idea about the liquefaction phenomena I have given you today, and in my next video, I will tell you the ways and means, the simplified method given by Seed and Idris, and our IS code method. Everything I will discuss in detail. IS 1893, Part 1, 2016, deals with determination of liquefaction potential by simplified method, and it is essentially the work carried out by Seed and Idris. So, in my next video, I will take a practical problem. Normally, you carry out a standard penetration test, field test, because the ground is going to be a granular soil. So, collecting undisturbed sample is not feasible. You should carry out the field test such as SPT, standard penetration test, or CPT, cone penetration test, or you can do shear wave velocity test. And then you can use IS 1893 Part 1 2016. This code highlights the simplified method based on SPT, based on CPT, cone penetration test, and also based on shear wave velocity. So all are the field test, and you can analyze and find out whether a particular ground is going to be liquefiable or it is non-liquefiable. If it is liquefiable, take the remedial measures. Thank you, friends. I hope a brief description of the liquefaction phenomenon must be crystal clear in your mind. So I thank you.